and Nyquist plots. In body plots, it's critical that you don't go too high in maximum frequency. Because if you go to too high maximum frequency, remember, things go to infinity. Both log AR and phi go to infinity as omega increases, and the whole plot with what happens around -180 is squished, so you can't see anything if you go too high in maximum frequency. In Nyquist plots, there's no problem going very high in maximum frequency because all you do is you go to the origin. So no matter how high you put omega maximum, you're not messing up the Nyquist problem. Minimum frequency, in this case, won't be a problem, but as we will see once we have integral action, we have to be careful about minimum frequency. Whilst in body plots, minimum frequency is not a problem, just do something small and you're fine. So, anyway, in this case, it won't be a problem. Everybody ready? Anybody needs more time? So, 0.1 the time delay, the coefficients here 1 and -2, 0 degree of A, and -15 A1. Click. Here is my +½ positive pole. And let me just say no, specific frequency. And let's use, in this case, I don't have integral action, so 0.001 will be fine. And let's put 100 for maximum, 1600 points. We can look at the body plot. -180, go down. It's probably around here. It's below 0. Are we stable?
Yes.
No.
It's irrelevant. Body plot tells us absolutely nothing in this case. If I ask you such a problem and I give you an open loop unstable, it's a trick question. Okay? You don't say anything. Okay, Nyquist plot. That's the one we need. So notice it will always start. Oh, there it is. Notice it started on this side now. And here's the spiral towards the origin. So you can see it doesn't have to start from the left, from the right. So that's the half contour, that's the C+. So first the C+ is drawn. Very important, as you know, the arrows. Which way does the arrow go? Since I'm adding here, the arrow goes this way. Okay? So careful, pay attention, it's also color-coded. Arrows for the dark brown curve ends at the origin. Should be pointing, ending at the origin. Do the full contour, you see the whole thing. Here is the C-. That's our Nyquist plot. So let me bring it into paint. Okay, I brought it into paint. Let's draw a line starting from -10. Actually, let's draw first the arrows. I want you to be drawing arrows. So remember, the brown line ends at the origin, so the arrow is in this direction, and the orange line leaves from the origin, so the arrow is in this direction. Clear? Important to figure out the directions. Got up? No computer?
Yeah, I do. I'm just looking.
All right, so let's draw a straight line. We can draw any straight line we want. from minus 1, 0. That red X that you see is the minus 1, 0. If the scale is such that minus 1 is not in this axis, just draw yourself an X outside here. Okay? Because of course it will only be drawn if it's within the scale. So I'm taking this and I'm drawing a line out to infinity and beyond. So which way am I rotating now? Center is that. Which way does it make me move? This way, right? The arrow moves me to the left. What's that? Counterclockwise. You can see now I said I will have an analog clock project on the screen. Don't mess up clockwise and counterclockwise. So it's a counterclockwise cut, right? So n is 0 clockwise, minus 1 counterclockwise, minus 1. So in this case, n is minus 1. So from minus plus, so z, which is n plus p, n is minus 1, p is plus 1, 0, closed loop stable. In all exams, you find an example, for example, the Routh array shows stable and the Nyquist shows unstable. All right? Clear on this, guys? So we understand the Nyquist stability criterion? Ashley, question? All right. But there's a complicating factor. If we don't have steady state offset, we need to have integral action, right? So we're going to be using, oh, that's not what I want to do. I want to do this thing. So, and with integral action, we have I erased the Nyquist path.
I have a question. How many different ways do we have to check if it's stable or not stable?
Open loop or closed loop?
Both.
Open loop, direct calculation of the roots of the polynomial or Routh array. Closed loop, possible direct numerical calculation, good luck with it. If it's open loop, stable body. If it's not, Nyquist. And for guidance, approximate Routh array with Padé approximation. That's what it was. The Routh array is still useful because the only thing that gives us guidance. Here I gave you 5. If you wanted to find a KC that stabilizes that, remember for Nyquist I need to have all the numbers here. So suppose the problem was design a controller that stabilizes the system. Okay? You could try different values and try every time Nyquist, but that can get old if it's a difficult case. And also, chances are, if the Routh array says that you cannot stabilize it, probably you cannot. The Routh array with Padé tells you there's no hope, then probably there's no hope. All right. So, Nyquist path, if I have integral action. Or I should say, if GU of S has a pole at the origin. Okay? So far, the Nyquist path at the C plus, the CR, and the C minus. But if I have integral action, GOL has a polarity origin. The PI or PID controller have denominator tau IS. So GC has a pole right at the origin. And that creates a problem of how we calculate with P. So what people are doing, they're modifying the Nyquist path to exclude just that one point. So the Nyquist path is modified. Now we have a little circle C delta. C delta has S equals delta into the I, another angle phi, where delta goes to 0, and phi, in this case, it starts from minus 90 and ends at plus 90. In this case, it's a counterclockwise. CR is clockwise. C delta is counterclockwise. Now, remember, we only have the C delta if GOL has an S in the numerator, in the denominator, like from integral action. So my GOL will be something, okay, 1 plus something e to the minus ds over S times other things. Because of the GC has an S in the denominator, GOL will have an S. Sorry, GOL, not one. GOL has an S in the denominator, not one. With me? So when I have S equals delta e to the I phi, that delta is in the denominator. What's the limit as delta goes to 0 of this? I have a 0 in the denominator, right? S is delta e to the I phi, and delta goes to 0. And S is in the denominator of GOL because GC has, remember GOL is G mu GC, and that GC has S in the denominator if I have integral action. With me? Clear? So since GOL has an S in the denominator, and in C delta, I have S is delta e to the I phi, but delta goes to 0, I'll have the denominator something that goes to 0. So where does GOL go? To infinity. As a matter of fact, C delta is a semicircle. Semicircle maps to semicircle. And it maps to an infinite radius semicircle. So C delta maps, and here's a very important fact. CR, if you recall in the plot, CR is actually going to be a zero radius counterclockwise. Very important part here. This is counterclockwise, but it's in the denominator, which actually, if you think the argument, you have e to the I phi, this makes it e to the minus I phi up here, which changes the direction. You change the sign of the argument. So it changes the direction. Since this is counterclockwise, C delta maps into an infinite radius clockwise semicircle. And that clockwise is critical. Another thing that happens is, before the Nyquist plot was closed just from the C plus and the C minus. Here, to close, it needs the infinite radius semicircle. So actually, C plus and C minus start from infinity. So a typical situation when I have integral action is that C plus could look, before we had C plus that were looking like that, right? Before we had C plus that looked, question? Shannon? Yeah.
Is there infinity radius?
Yeah, infinity. That's a badly written infinity. Infinite radius clockwise semicircle. Yeah. The zero radius semicircle maps to an infinite radius semicircle. Before we had the infinite radius semicircle, it was mapped to a zero radius semicircle. Okay? Might have some beauty. So before, our C plus was looking something like that. Now, our C plus will look possibly something like this, coming from minus infinity possibly. That would be a possible C plus. Or it could be coming from above. That could be a possible C plus. But it's coming from infinity. Because if you take omega 0, that omega 0 in the denominator, that is in the denominator blows up. So it's coming from infinity. So C plus could be this. In which case, if this is C plus, what is C minus? The mirror image. C minus would be that would be C minus. If it's coming this way, if this is C plus, what would be C minus? It would be going that would be C minus. Okay. What makes the curve closed? Making up with you're very tired. I exhausted you. Sorry. Still have face.
That'll make it better.
Okay, so that's, I could have C plus this way, C minus this way, and then the curve closes with an infinite radius semicircle. Key question. Which way is the infinite radius semicircle? Let's say minus 1, 0 is here. If the infinite radius semicircle is on this side, then any cut would have, any line would have cuts. If it's on this side, I can draw something that doesn't have cuts. Because cuts should include cuts with the infinite radius semicircle. Okay? For the Nyquist-Stability criterion, you need to include cuts with the infinite radius semicircle. So it's key question which way I draw the infinite radius semicircle. I could draw it this way, or I could draw it this way. Who will tell me which of the two ways is the correct one? Okay, Thomas points in the right direction. Thomas says this is the correct infinite radius semicircle. And he is right.
Because it's clockwise.
Why?
Because it's clockwise semicircle.
Exactly. The circle, the infinite semicircle, has to be clockwise. And arrows must not collide. Let me write that down. Arrows must not collide. Double L for collide? Yes. If I did it on this side, clockwise, because I can do it clockwise, this side or this side, but it has to be clockwise.